So let's start the lecture. In the previous class, we learned a little bit about tree. A tree is a powerful but very simple and intuitive model in classification. It's more general than classification. Tree can be used for regression as well. And that was the setting of our problem, that we had n data points and our points were d-dimensional, and we defined this capital X as a matrix of all of the data points, which is a d by n matrix. And then when we want to refer to a feature of the data, we refer to one line of this matrix, which is basically xj dot. I mean the jth row of this matrix, which is a feature, and x dot I is ith column of this matrix, which is a data point. So this is feature or variable, and this is data point. Okay. So the concept of tree was very easy and intuitive. And the idea was that let's divide the space to different regions and fit a very simple model to each region. So basically, I can simply, start dividing the region to two half regions by doing, split at some certain xj. So I decide that if xj is less than a threshold, I'm in one region. If it's more than that, I'm in another region. And then I continue doing this on different xj's, okay, until I have small regions and I'm confident to fit a simple model to that small region. That simple model could be a linear model, could be a constant even, okay? Or in classification, I can just assign some sort of some label to that region. I can decide that every point in this region has shared the same class label. To do this, actually, the whole idea is to decide about the feature that I want to split and the threshold. So I have d different features. Which one should I choose to split in the first step? And when I choose one of these features, say I have chosen x3 to make the split, where should I put this my threshold, to make two regions? So to do this, actually, we decided to minimize a cost function. And, let me first tell you that when we split, we have two subregions. I call one of them R1. And R1 is basically set of all points such that the feature is less than or equal S. And R2 is set of points such that their features is greater than S. Then we minimize a cost function, and this cost function is basically, a cost over all points in region 1. So for all points in R1, I try to this is just a simple cost function It's good if we want to do regression, for example. If you want to do classification, we may choose a better cost function here. But for the moment, for simplicity, assume that this is our cost function. We are going to generalize this cost function to any cost function later on and see if you want to do classification, what cost function would be a better one, better than this one. So this is basically the cost function that we would like to minimize. And by minimizing this, I would like to find S, and I would like to find J. Basically, I need to know, because giving a J, I'm going to, and S, I'm going to make two subspaces, like half spaces. And so I have to choose the optimal J and optimal S, which minimize this. Means that I have two parts. I splitted the space in two parts. I would like all of the points in one part be represented by a simple model like C1, which is a constant. This could be a linear function, for example. It could be anything. But a simple model. And this is another simple model. Okay, so we discussed this objective function in the previous lecture. Is it clear? The objective function that we are trying to minimize? Okay, so a very simple procedure actually to minimize this cost function is to go over all possible J's and all possible S. Okay, we can constrain ourselves to choice of S. Basically, I have D possible J's. So x1, x2, each row of this matrix could be one of the features that I can split. And if I choose one of these xj's, then it's a vector of length n, one of the row of this matrix, right? So I can choose any element here as a candidate for S. I can split over that value, okay? So basically, I can start from x1, and in x1, I have n different possibilities for a split, and I can compute the value of this cost function for all of these cases. There's n possibilities if I choose x1. Then if I choose x2, there are n possibilities. If I choose x3, there are n possibilities. In total, there is d by n possibilities. And among all, the one which has the minimum value is the one that I have to choose. And don't forget that this is basically this minimization. Already I know inner minimizations, we know the answer. It's just, C1 is just average of yi such that xi, or let me write it as xi is in R1. So basically, if I take the average of all of the yi's in region 1, that would be C1. And all of the yi's in region 2, that would be C2. So inner minimization, we know the answer. So if I choose D by n different possibilities, I can decide which feature to split and where. Where should I put the trash? This is the simplest thing that you can do. There are many variations and much better ways actually to reduce this cost instead of checking all of these possibilities. There are techniques based on like information gain, for example, among all features. Which one you're gonna gain more information? Which one is more representative for the task that you want to, the target value. Or there are all techniques of feature selection among all of these D features. Which feature is more representative? Let's start with that one. And don't brute force all of these possibilities. Okay. So here actually, everything else is going to be quite clear. I can grow a tree this way. then we came to this question that how large a tree should be. Because I can keep going and splitting regions to very small regions and reduce these functions. But at some point, I have to stop, otherwise I'm going to overfeed the data, because I can go as small as 1 point, and this is overfitting. This is memorizing the data. We don't want to do that. We need a model. And the more obvious thing that you can do is cross-validation, that you can set a part of the data aside, and when you are growing the tree, check the performance on that part, the validation set, and stop if validation set start to increase. Okay, that's the most obvious thing that you can do. Also, we discussed that another thing that you can do is to decide on a spot. I think I can split on x3, but I have to check if x3, how much x3 is going to decrease my whole cost function, and set a threshold. If it's not more than a threshold, then I will decide that it doesn't worth it to go this path. I'm not going actually to bother splitting here, because it's going to improve it, but not that much. And we discussed that it's a bad strategy. We don't want to do this, because it might be the case that x3 is not good split, but it leads to a good split. Then x4 comes after that, and that's a good split. And if you don't do that, don't do split on x3, then you're never going to see x4 as a good split. So you don't want to do it. You want to maximize your long-term reward, not short-term reward. Okay? But the most common and most successful way is pruning. And pruning works this way, that you grow a tree and you don't care about overfitting, You just try to minimize this. And you make a big tree, grow a large tree. So let's call this large tree T no. So I grow a large tree T no. Okay? Then I start to collapse nodes of this tree, basically prune this tree, make it smaller, and select a tree which minimizes a cost function. That cost function is basically a regularized cost function. So it's a cost function plus a term, which is a factor of complexity of the model, the tree. And this also we discussed, that would be cardinality of T, size of T. But by cardinality of T, we basically mean the number of terminal nodes, the number of leaves. Okay? So basically the number of regions that we have. We don't want to have many regions here. Okay, this part, this cost function, can write it as NM times QMT. For M equal to 1 up to the size of T. So I would like to minimize this cost function. And there is a factor always here, alpha. Okay? So I would like to minimize this and find T. Here actually, NM is the number of points in region M. And QM is 1 over nm sigma yi minus cm squared for all xi in Rm. See, I splitted the space in different regions and say, for example, this region is region M. In this region M, I'm going to compute this cost, the distance between yi and my model, my observation and my model, how far they are, over all points in this region, and then they take the average, divide by the number of points in that region. So it's basically error of this region, okay? And the total cost would be the error of all regions, m equal 1 to t, for all of the m, when m basically represent a region. Okay? So now the idea is quite simple. You have a large tree, T0. The T that we are going to choose is subset of T0. It's not any tree, it's a subset of T0. What we are going to do is to collapse nodes and make different T's by collapsing nodes. If I have, a large tree, and these are all different nodes, I can decide to collapse some nodes and make a tree which is simpler than the existing tree, and collapse some other nodes and make a tree which is simpler than this. Okay? But I will collapse the nodes based on checking that how much when I collapse node, this cost function is going to increase, right? Just look at this part. If I have a very large tree, this is small. Then I start to collapse node. It starts to increase, right? So I'm going to decide which node should I collapse such that the amount of increase here is minimum. Okay? Collapsing nodes means merging regions. I have so many regions. I would like to merge 2 regions and make it 1 region, right? Which 2 should I merge such that the amount of increase in this cost function is minimum? So basically, we start to collapsing nodes that has smallest per node increase. Means that it has the smallest nm qm t increase for that node. Yes? You mean this function and that function? No, see, I have, m is my index. When I say m equal to 1, I refer to region 1. M equal to 2, I refer to region 2. How many regions do I have? Cardinality of t, because that's the number of terminal nodes. number of regions, right? So basically, on each region, I compute this value and add them up.
So they are the same?
No, they are not the same. This is when you want to split. It's only about 2 regions. At this split, I want to minimize it. It's just 2 regions. That's over all possible regions. That's all regions. That's local. That's global, you know. That's the cost for a tree that I have made. That's the cost at one split. Okay, so I'm going to basically decide which nodes should be collapsing. Okay, so collapsing nodes make a new tree. Starting from T0, I can have a path, you know. I can decide, okay, this is T0. Then which 2 nodes should I collapse that increase my cost function for a small value? I'm looking for the smallest value. And I'm going to find those nodes and collapse them. Okay? So it gives me a new tree. Let's call it T1. On T1, I'm going to do the same. You know, which nodes should I collapse such that it gives me the smallest increase on my cost function? It's going to be T2. And it's a sequence. On this sequence, I'm choosing the one which minimizes this cost function. Okay? So the one which minimizes this cost function is my optimal tree. And this path is a unique path. It's not that if you run it 2 times, you're going to get 2 different paths of trees. It's a unique path. It's completely deterministic to decide which 2 nodes should be merged, should be collapsed. So the T that we are going to find this way is unique. Given a T null and given alpha, it's going to give us a unique T. So there is one tree which minimizes this. Yes?
The nodes that collapse, is that necessarily those regions that have fewer number of points?
No. No. The one which minimizes this. The number of points has effect, you know. We're going to see that, you know, when you have a smaller number of points, the increase will be smaller. But that's not the only factor. Any question? Okay. So that was completely general. And you can do it for regression, for example. If you want to do classification, the only difference is that you may choose a different cost function. You know, you may choose this cost function for classification. Doesn't matter, but it's not a common cost function for classification, because in classification you have categorical data. You have either 1 or 0 or 1 or -1, and you need a cost function to decide, you know, your distance from the true value better than just norm. Right? So let me define PMK to be 1 over NM sigma I that yi is equal to k, and for all xi in Rm. And here we do classification, and yi is set of all possible classes. Suppose that I have k classes. I have k classes, so it's categorical data. Data can come from any of these k categories, and I define PMK to be, you know, this is basically identification function. So it's going to be 1 if yi is equal to k, and 0 if yi is not equal to k. So PMK basically is going to be the percentage of the point that are in class K in region M. Okay, so suppose that I have two classes. In this particular region, some of the classes are plus, some of them are minus. So I will count the number of points that are plus. 1, 2, 3, 4, 5, 6. That would be 6. Divide by total number of points. 1, 2, 3, 4, 6, 10. 60% of the points are in class plus. 40% of them are in class minus. So that's basically, it shows how pure is that region, the percentage of one class in that region. Okay? And PMK stands for pumpkin, for Halloween. Okay, so that's basically a measure of purity of a region. Purity of region M for label K. Now, okay, what would be a good cost function? Cost function that we used many times so far was misclassification. You know, how many points? Basically, in each region, we would like to minimize misclassification. We don't want the points to be misclassified. We prefer that, you know, because for each region, I'm going to assign a simple model. This simple model and classification would be just labels, right? So I prefer a region be pure. All of them be from class plus. All of them be class minus. So I don't want a mixed class in pure class. So I can define misclassification, for example, which is basically 1 minus PMK. And if I take the summation of that over all region, right? So that would be misclassification for class K. So I may decide to minimize misclassification. There are three very common measures in decision trees. One of them is this misclassification. Another one is this summation of PMK times PMJ when K is not equal to J. You know, consider that you are in a region and you have two types of classes. And P is basically, you know, the percentage of class label K. This is percentage of class label J. When this is going to be maximum? Sorry? I can't hear you.
When those two PMK equals to PMJ?
When they are equal, yes. So it's going to be maximum if they are equal. If half of the region is from class K, the other half is J. That would be maximum. If I start to, in the best case is that I have only K and the other one is 0. Or I have only J and the other one is 0. That would be minimum, right? That's another cost that you can define. You know, misclassification is part of type of cost. This is another type of cost that if they're mixed, it's going to be large. If they're pure, it's going to be small. And cross entropy is also another measure, which is basically PMK and log PMK. So let me show you a graph here which shows the relation between these three measures. This is PMK or whatever, PSJ, and just different notations. This is just in the number of points in one region and the number of points with a particular label in that region. Then these are these three famous one that I told you. And if you look at the graph of them, assume you have only two classes and assume this x-axis is percentage of second class. Here means I don't have any point from the second class. Half of them are from the second class and all of them are from the second class. Then misclassification has this shape. It's linear. So misclassification will be maximum if half of the points are from this class, the other half are from the other class. This one also, as we see, get maximum, the green one, when we have half-half, and entropy also will be maximum as half-half. So there are these three different that they're common in the literature and people use. And here actually entropy has been rescaled to match these two. It's not, doesn't get to 0.5. Any question? And there are different type of trees like CART and ID3 and C4.5 and C5 and many different variations of tree based on how you start, choosing the variable to select, how you choose the threshold. But the basis of all of them is what I explained to you, Okay. There is also, a very famous concept, forest, random forest. And random forest is basically sort of averaging or weighting or taking the majority vote between many trees. So as you fit different trees on different part of the space, not on the whole space. So you have different models. And then somehow you take average or you take majority vote between them. So we will talk about it in more details later on because it's basically bagging. When we talk about bagging and how bagging in general for models work, then we're going to see, and we see boosting as well, then we will talk about forest, random forest. Any question? Okay, let me show you an example here. So here is an example on the data set that on assignment and in class we've worked with like 2 and 3 digits. Okay, so here in the first part of the code I just load 2 and 3 and so you can see that this is 64 by 400 matrix. So dimensionality of the data is 64, and we have 400 data points. The first 200s are 2, and the second 200s are 3. Okay, so if I visualize like x1, say for example, and reshape it to 8 by 8. This is 2, okay? So this is more clear, I think. There are different 2s, and after 200, there are 3s. Okay. So we have seen this data set before, and we would like to do classification on this data set. So I just loaded this data, and the next thing that I'm going to do is to apply PCA on it. You know, I just take the mean out and then apply PCA on this, and then my new data would be two-dimensional, you know, when I apply it. So return. Here is the data. Okay, if red points are 2 and blue points are 3. So if you want to fit a 3 to this data set, you have two possibilities, two variables, x1 and x2. So you can make a split on x1, or you can make a split on x2. Which one you're going to choose? Which one is going to minimize this? Here, actually, you know, this cost function is for classification, so it's not a squared error. It's like how pure each region is going to be. So x2, right? x2 would be the choice. You know, I have to make a split here. And where you're going to split it? Close to 0, right? Somewhere close to 0. If you split, you're going to have two spaces. But then there are regions that you haven't covered. You know, there are many points that are going to misclassify. So you can grow your tree more and capture those points. But there is a threat that you overfeed the data. Okay? So I just feed a tree to this data, and the tree looks like this. You know, there are many terminal nodes which basically tell me in region 2 or region 3. And if you look at the first decision is at x2. And we visually saw that it should be close to 0. You can see that it's negative 0.08. Somewhere close to 0, you had the split. So it's a pretty large tree, and most likely overfitted the data with this tree. So we have to prune the data, prune the tree, because it doesn't look. So here actually is the regions that this tree makes, and with the data points. You know, the green, the red are when this tree decided that it's 2, and blue where the model decided that it's 3. So it's quite clear that it's overfitting. You know, I had only one data point here, and this model decided that this region is 2. And, you know, at the middle of region 2, for a couple of points that I had, decided that this part is 3. Decided that this part is 3. No way that this is going to predict well, okay? because it's clearly it's overfitting. So we have to prune this, and if I prune this and if I look at the error rate, when this is the number of terminal nodes, you can see that with more terminal nodes, the training error becomes smaller and smaller. This is the notion that we had before. But at some point, the test error starts to increase. And this is where actually, where the number of terminal nodes is 2. If I have more than 2 terminal nodes, then the number of, the value of test error is going to increase. So 2 terminal nodes means what? Just one line, So the optimal tree in this case would be the just draw a line. So that would be the tree after I prune it. It's going to be only 2 and 3 on one line, and that would be the decision boundary. So it seems that this is going to perform the best on test data. So between these 2 extreme values that I have only 2 nodes and I had many nodes, you can, when I learned this tree in MATLAB, I call it T, then I can prune T with different values, according to this graph that shows the training set and test set. I have a variable here which is called best level, and it turned out that the best level is 5. So I prune it this way, and then I can visualize this was this tree. But I can prune it like this, for example, and then I view it. It's a tree of this form. It's not as complicated as the original tree, not as simple as the last tree, and if I visualize the regions, see, it's not just a simple line. And hold on, and let me plot the data as well. So now we decided that this part is also class 3 because of these points, So we decided the decision boundary is here, for example. But it's not as good as the previous one in terms of tester. Okay, any question? Okay, let me show you also another example here. This is this data set that we had before. And so the model is going, the tree is going to decide that we have this many regions, and that will be previous time. Okay, with that tree, this is going to be regions, you know. There are only a few points that have been misclassified. Okay, what's going to happen if I try to prune this tree now? Do you think it's going to give me a simpler model? You know, that's going to be my graph. It seems that the more terminal nodes that I have, the less error on training set and on test set, both of them, I'm going to have. So if I try to prune this tree, nothing going to happen. That the tree is going to be the same as the original one. So see, these two trees are identical. And it's going to give me the same region. Okay, the reason is that if you remember when we talked about Stern's unbiased risk estimator, when we computed Schur, the error, we had, we had training error, or we had basically the true error is training error, and we had a constant, and then we had a term, and this term was derivative of f hat with respect to observation, but we had a coefficient here. And coefficient here was sigma, which was, do you remember what was this? It was variance or a standard deviation of noise. So in the model, our setting was that yi is f of xi plus some noise, and this noise was normal 0 sigma square. Okay? And that was the variance of this noise. So basically, our assumption was that if there is this model, f, what we observe is not exactly samples from the model, is samples from the model, then some noise has been added to this. And then if you try to accommodate all of these observations, you are going to overfit. Basically, you are going to feed all of these noises. If there is no noise, if the model is noise-free, if it's completely a smooth function, and you don't have any noise here, then this term is going to be 0. The last term, ensure, is going to be 0. And your true error is, your training error is an estimation of the true error. Does it make sense? So what happened here is was the same thing. We had this perfect circle without any noise. It never happened that, one of these red points appear here, one of these blue points appear here. And it doesn't matter how complicated your tree is, make your model as complicated as you want. It's not going to overfit because there is no noise, right? But it's not realistic, it's, it's artificial data that we made. In reality, noiseless data doesn't exist. Always our observations are noisy. So I can add some noise to this, and then things will be different. This is labels of classes. One are red points in inner circle, and two are blue points. So let's add some noise to it. If I add noise, say 10 to 15, for example, that's supposed to be 1, I set them to 2. Or 199 to 195, I set them to 1. Okay? So the data is noisy now. You can see this, or you can see this blue here. Then it's going to find a complicated tree and complicated regions that clearly is overfit. But if I prune this, then I'm going to have this region, compared to the previous one that, it captured all of these noises. One regularization technique is to add noise to input. It's used in neural network quite often. You want to regularize neural network, you add a little bit of noise to input. Like in autoencoders, it's used a lot. If you give perfect input, if you give input X and output X, that it's going to overfit, and then basically add a little bit of noise to it. Okay, any question? Yes?
Important that here we didn't consider the Gaussian distribution of the noise.
Sorry?
What distribution did you consider here? Because you just changed some node, some number. So is it Gaussian or not? Because here we discussed the noise must be Gaussian.
No, it's not Gaussian. It's, the noise, in reality, the noise is not additive. The noise is not Gaussian noise. Don't forget, all models are wrong. Some of them are useful. This is just a useful model, but it's a wrong model. In reality, the noise is not Gaussian. The noise is not additive. Just we make this assumption because we can't do better than this, And we just assume that if the noise is additive, if the noise is Gaussian, then this is my analysis. But in reality, no, this is not Gaussian noise that I added. Just noise. Okay? Okay, so I promised to cover a couple of simple classifiers that we haven't seen. So one was tree that we learned about. The other very common classifier, but very simple classifier based on the knowledge that you have now, is naive Bayes. Okay. You remember that according to Bayes' rule, the classifier that we have to find has to maximize class conditional times prior, right? Because Because according to Bayes' rule, probability of y being k given x being x is just p of x given y, which we show it by fkx. That's class conditional, right? Times prior, which is py, which we show it by pi k, divide by p of x, which is summation of fk pi k over all k. And this is constant, this regularization. So if you want to maximize the posterior, you have to maximize this quantity. And that was Bayes classifier that we started with. And in Bayes classifier, the first thing that we did was to assume that this class conditional is Gaussian. It leads to linear discriminant analysis and quadratic discriminant analysis based on the type of assumption. So it's Gaussian. So naive Bayes is Bayes classifier with a naive assumption. The naive assumption is that this fk x can be written this way. You know, because in general, if fkx, okay, if x is d-dimensional, is what? It's a density over x1, x2, up to xd, right? So if I want to decompose this, it's what, in general? Don't make any naive assumption. Sorry? Yeah, this joint distribution, write it as conditional distribution over each of these. Yes?
Probability of one times the conditional probability of that one, and the next one, and the conditional probability of the third one.
So I can write like probability of or density of x1
Right.
times x2 given x1, right? Times x3 given x2 and x1, and so on. You know? And fd given x1 up to xd. That's in general. So let's make a naive assumption, and the naive assumption is that there is no conditional dependence here. So I can write it as fx1, then x2, because I assume that x2 is independent from x1. I assume that x3 is independent from x2 and x1. So basically I assume that it's fx1 times fx2 fxd. It's quite naive assumption, but as I told you, all of the models are wrong. Some of them are useful. It's a useful model, but wrong model, you know, with naive assumption. In reality, you can't assume this independence, you know. There's dependency between these variables. But let's assume that they are. So in terms of classification, okay, if you make this assumption, then it's going to have a very simple form, you know. It's just product of, you know, you have a multivariate distribution that you need to model. It means that you can have the single variate distribution, and the product of all of these d single variate distributions is going to be your multivariate distributions. Estimating multivariate distributions is hard. Estimating single variate distribution is easy. You know, in any sense, if you want to do density estimation in one dimension is easy. In d dimension, it's hard. You can make also simple assumption that on each dimension it's Gaussian, or each dimension is Bernoulli, and you have a question in your assignment that you make one of these assumptions, in fact 2 assumptions, and you're going to derive the final classifier and see the form of final classifier. You will see it in your assignment. But that's the idea. What does it mean in terms of classification? In terms of classification, it basically means that I have a random variable y, and I have a random variable x. Okay, so this is a vector, right? So I'm going to assume that this vector has no dependence between each feature. So when I want to write the joint probability, it's going to be P, basically, P x1 given y, P x2 given y. So there is no interaction between them. In fact, it means that each feature by itself basically lead us to make a decision, not combination of these features. You want to decide that this person is going to have heart attack or not, and this is blood pressure, this is cholesterol, this is the history of this person, the fact that this person is a smoker or is not a smoker. So naive Bayes assume that each of these features by itself, can lead to a decision. You can make decision based on this or this or this, and then combine them, but not the combination of these. It doesn't matter. In fact, it does matter. In fact, combination of having high cholesterol and being a smoker is important. To know that these two features at the moment exist. It does import. Okay. Okay. So any question about naive Bayes? So another simple classifier is k-nearest neighbor classifier. And k-nearest neighbor classifier simply means that I give you a test data point, and you want to decide about the label of this point. You basically look at the k-nearest neighbor of this point and look at the labels of those k-nearest neighbor and take majority. K is parameter of the model. Could be 1, means look at the 1 nearest neighbor. Could be 10, look at the 10 nearest neighbor. And assume that it shared the label of the label close by. And the neighborhood, all of them are 1, so most likely this is 1. Neighborhood, there are 3, so it could be 3. As simple as this, this is k nearest neighbor. Just look at a neighborhood, take majority. So k is a parameter of the model, it's complexity of the model. So k equal to 1 is more complex, or k equal to 10 is more complex? Sorry? K equal to 1 is more complex, The larger the k is, the more simple the model. How can you overfit? How can your decision boundary be so wiggly? If you're not stable at all and you just look at the neighbor close to you, okay, this is 1, I claim 1. This is 2, I claim 2. But if you take a majority of more points close by, it's way more stable, more smooth model, So the less number of points you take average of, it's less smooth. So it's more complex, more flexible. So you may think that it's not a good model, but that's not the case actually. In many cases, k-nearest neighbor, a model as simple as k-nearest neighbor can produce a good result. Here is you know, this is artificial data, and this dotted point is base bound, you know, because we generated data, we can compute the base bound. I mean, we generated data, it's a mixture of Gaussian. Mixture of a couple of Gaussian, we generated this data, okay? We know the class conditional, we know the prior, we know the marginal, we know everything. So I can exactly draw the base bound. So the base bound, if you remember, was the bound that you can't beat it. You know, it's impossible to do better than this. So this is the bound that you can't beat it. It's impossible to do better than this. And this is what K-nearest neighbor for. You know, it's pretty reasonable boundary. Okay. The problem with K-nearest neighbor is that it has high frequency usually, and it depends on the number of high variation, sorry, and it depends on the number of points that you have. You know, it needs many points to be stable. But asymptotically, if you have many points, you can prove a very good bound for K-nearest neighbor. You can show that worst case, it's 2 times worse than base bound. You know. But asymptotically. Asymptotically means if you have, I mean, means nothing in practice, actually. It means that in practice, it's not something that you can trust. But, and you know, this is when K is smaller, is not as smooth as this one. It's large K, this is small K, you know, it's not as smooth as that one. Okay, so you can kernelize K-nearest neighbor. So we have seen like kernel variation or kernel version of some algorithm, and K-nearest neighbor also can be kernelized. So K-nearest neighbor works based on distance of your point, your test point, with some other training points, right? So you usually compute the Euclidean distance, which is xi minus xj transpose times xi minus xj. So if you want to find the Euclidean distance between point xi and xj, you compute it this way. Okay, you go with k nearest neighbor, the k points that have closest distance in terms of Euclidean distance. So I can kernelize this. I can map all of my points to some feature space. And then compute the distance between points in that feature space. So the distance between points in the feature space would be phi xi minus phi xj transpose times phi xi minus phi xj. Now, it's going to be phi xi transpose times phi xi. And I'm going to have a term phi xj transpose phi xj. And I'm going to have -2 phi xi transpose phi xj. All of them are kernels, you know, they are dot products. This is dot product, I can represent as kernel, dot product, dot product. In fact, if I have a K as n by n matrix, okay, such that Kij is similarity between xi and xj. This expression here is simply going to be kii plus kjj minus 2 Kij. So kernel k nearest neighbor is very simple. You have n data point, compute a kernel over these, say Gaussian kernel, for example. And then you're going to have n by n matrix. Now the distance between 2 points xi and xj would be kii plus kjj minus 2 kij. So 3 entries of this matrix is going to be your distance between 2 points in the feature space. So choose the k nearest neighbor in the feature space. That's it, you know. The rest of the algorithm would be the same. Just choose your point based on their distance in feature space, not in the original space. And there are many like fancy algorithms in metric learning. If you remember, in metric learning, you find a transformation of the data to map the data in a new space such that that space has some properties which is better for your task, your classification, for regression. An interesting algorithm about k nearest neighbor is called maximum margin k nearest neighbor, like maximum margin classifier in terms of support vector machine, that they find a classifier which has maximum margin to both classes. It finds a kernel for the data. Basically, it maps the data in a feature space such that in that feature space, if you have, you know, this is my space, you know, I have some classes. All of the neighbors or 4 nearest neighbor of this have the same label, but there is also one point here that is not belong to this class. If I take the majority, when I want to classify this point, say I want to classify this point. If I take the majority, it's going to be plus, but there is one here which is minus in the original space. So this maximum margin k nearest neighbor find a space such that it's going to put, you know, a circle around this and force points that doesn't match the majority outside. Force it out. Basically find the transformation to force this out. So this nearest neighbor would be clean. So they have maximum margin. So it's pretty interesting in terms of theory, but it needs to solve you know, a complicated optimization problem, semi-definite program, so it's not practical for large data. So people don't use it in practice when they want to do classification, but it's interesting. Okay, any question? Okay, see you on Thursday.